Thank you, Professor, for your introduction. So, to date, the printed circuit board assembled are present in many systems. So from the electronics to the aerospace, but all of these components base their life on a linear economy model. So at the end of the PCB life, that is destined to end up as a waste. So what the designer can do is to prevent the premature mechanical failure of these components. But we have to underline that for a single board, it's possible to have also 10 different professional figures. So sometimes the communication flow is not very smooth, and the risk of errors increase very significantly. The design involved two main sectors. First of all, of course, the electronic designers, and for the second, the mechanical designers. But the first not only create the electrical circuits, but also select the component and the layout of the component. So how the component are put on the printed circuit boards. So at the end, the mechanical designers have already defined the layout. So at the end, can only assert if the PCB assembled have a success in a test or not. So what we want with this research activity find is a support tool for both, so the electronic and the mechanical designers, that obviously, given the preliminary knowledge of the PCB and the applied input loads, and from a simple data sheet of the component that we want to mount on the PCB, we want to returns with a map of the area that are usable for put on the component. So we start with the classification of the components. We have two categories: the surface mount technology and the through-hole technologies. And if we compare these two assembly methods, we can assert that the through-hole technology involve very massive component, and these components are that put the PCB in a failure case. So if we focus on these components, and in particular on the radial leaded components, and you can see in this figure a schematization of that. And if we put an hypothesis that the boards are excitated by a parallel load to the foot of the component, the scientific literature is in agreement on how this type of component breaks down. So the curvature of the PCB returns with a constant displacement. So we have a bending and a normal stress on the lead of the component. And we have also to add another stress that depends on the dynamics of the system. So if we model the component as a mass spring damper system, we have also to add a normal stress due to the displacement between the mass and the PCB due to the excitation at the frequency resonance of the system. Another thing that all the literature is in agreement is the failure point. That is always in this part, so very near to the solder. From Steinberg to the NASA report, all report that the failure is in this point. So we want to now illustrate the workflow of our proposed approach, and the input parameters consists of the knowledge of the PCB. So we have to know the Young modulus, the Poisson ratio, and the density of the PCB, but not only, also the external connection, but are all the parameters that the designers know at the beginning. So after that, we have to know the input, so like a power spectral density of the acceleration in the input, and the duration of that. And another parameter that we have to have is some parameters that come from a data sheet of the component. From these two input, we can enter inside a finite element software, simple, and from the dynamic of the system, we can record the power spectral density for each point of the displacement of this. So the displacement of each point of the PCB. And with this, we can calculate with the RMS value the maximum deformation that the system can have. So at the end, we have this 3D plot that is the maximum deformation of the PCB. With the knowledge of the body dimension, in particular this length, so the biggest one for the component, the algorithm, and this is the heart of our approach, takes each plane in the maximum slope direction and put the segment L in this direction to calculate the displacement of the PCB, of course, at the end of this segment. So at the end, what we have is, for each point, the maximum constraint displacement of the PCB. And with this, and with the knowledge of the fit geometries, we can arrive with the Wheeler curve of the material of the fit of the component to the damage that this displacement produced to the component. So this is the first part of our total damage, because we have also returned back and used the power spectral density of the displacement also to as an input of a single degree of freedom that model our dynamic, the dynamic of the component. And so also in this case, calculate in very simple way, the maximum mass displacement. So this part produces another damage, because we can assert that we have now also again for each point the maximum mass displacement, and with the knowledge of the geometry, we can analyze the system, and with the Wheeler curve of the material, again, the damage that I called second damage, because it's the second part of a total damage that comes from superpositions. So at the end, the designers, from a graphical point of view, can select a tolerance range for the safe and for the critical zone. And of course, the green one is the safe zone where you can put that component, and the red one is the critical. Planning the experimental test campaign was not very easy, but we start from this simple 6-layer PCB. And we use this component that is a relay, and put on the center of this PCB our relay, and decide to have 4 input that are 4 power spectral density in terms of acceleration, that have 4 RMS values, so 4 level, and for each of these we test 2 PCBs. We test it in a head of a shaker. So we put this input on the shaker, and we record out the electrical voltage of the component. So we monitor if is voltage return back or remain to zero value. When remain to zero, we are the breaking instant. So we can record this time, and at the end we can use it. Also, the failure location is like the literature. So all the component, the failure point of the component is immediately downstream of the solder joint, as indicated by this figure. And Steinberg, that is the most literature that represent this approach validated. So if we put the experimental test in a graph where we have the RMS value in input and the number of cycles, we can find that the failure points are distributed linearly, and what this is due to because the phenomenon is governed by the fatigue of the material. So it's like a Wheeler curve of the material. And so now how can predict this? We have the input, so we have the knowledge of the PCB because we have also previous some tests on that. So we know the PCB, we know the component, and all these parameters that come from his data sheet, and we know the Wheeler curve of the material of the feet. And now we know also the time, the breaking time of this for input. So we have all the inputs of our theoretical to theoretical predict the failure, and at the end we can exit with this color map. So the point where the component had been placed turned out to be critical, yes. And so the methodology would have alerted the designer that if you put the component in the center is a not correct place. Okay, but if we analyze better the damage, we can assert also that the error is about the 32%. So in that point, the error is too big, okay. But at the end, even if the mean value of the error on the prediction is about the 35% that exceed the typical industrial design standards, is for us acceptable because of the goal of our research activity. So the results indicate that the proposed methodology provides a good support during the design of printed circuit board assemblies. So the future development is, of course, to implement this methodology on a different type of components and generate an user-friendly interactive tool. Thank you for your time.